So good day, ladies and gentlemen. I would like to welcome you to this new channel. I will talk a little bit later why this channel. First, I'd like to introduce myself. My name's Wojak. I know there are a lot of Wojaks out there, and I'm the plant science Wojak. I would like to welcome you to the first video of the PH series in hydroponics. And in the first video, we want to talk about what a molar concentration is, because when I talk about hydroponics, I always think in mole units, and in this video, you can learn how to do that and why to do that because it's useful. So stay tuned. So first, we need to talk about what is a mole. And by the way, excuse my deep, scratchy voice. I'm still a little bit sick. So a mole is basically just a number. So we have a pair, that is 2. We have a dozen, that is 12. And a mole is 6.022140076 times 10 to the power of 23. So basically, it is a very, very large number. And of course, it is related to chemistry because when we talk about hydroponics, when we talk about nutrient solution, we talk about what is inside the solution. And we want to express that in molar units because this is very useful, as I've just said. And let's first start with what is behind the mole and that basic chemistry thing. So guys, why mole? Well, look, when you look in the periodic table, you find all atoms. And I'd like to explain you by the example of chlorine. Let's break down what information we have here. So of course we have the symbol, we have the name, the chemical group, which is also the column in the table, and we have that continuous atomic number, and we have the atomic mass, which is in our regard when we talk about mole, that what we require. So long story short, 6.022 and so on chlorine atoms have a weight of 35.45 gram. And we can do that with any atom. For example, hydrogen has an atomic weight of 1. So we can say that chlorine atoms, they are 35.45 times heavier than hydrogen atoms. Okay, so why mole? It's a different way of comparing. You know we take, and this is what you should take away. We could also take half a mole or 10% of a mole, and then we always result in a different mass for these number of atoms. But in the periodic table, you find the atomic mass for 1 mole, okay? And it's like a different unit for atoms and molecules. Of course, any atom needs to have a mass, and every molecule needs to have a mass. And we can compare, for example, let's take a salt like sodium chloride, and let's compare it with sugar. I mean that sugar that you put in your coffee, which is sucrose. We could also take glucose. It doesn't matter. We can count any atom or molecule and say 1 mole, which is that number, has a certain weight. And that's basically what a mole is and what that atomic mass tells you in the periodic table. So let's make some more examples. You see here we have a section of the periodic table: carbon, nitrogen, oxygen, silicon, phosphorus, and sulfur. So 1 mole of nitrogen atoms is 14.007 gram. That was easy because of course you find the information in the periodic table. We have to consider, by the way, that elemental nitrogen, it always comes as N2. It looks like this. Oh, that's the wrong color. So there is a strong bond between two nitrogen atoms. This is how they are in the air. So if someone ever asks you what's the molar weight of nitrogen, then you need to say 28 because they always come together with this in elemental form. That's, by the way, also true for hydrogen. But that's not so important. So another example, sulfur atoms. We have 32,007 gram. And now we could, for example, also calculate what's the weight of one atom. So we just need to do 32.007 gram by 6.022 and so on. And then we find out that one sulfur atom, of course, the weight is very, very, very low. But just that you understand that when we have that atomic mass, that we can calculate the weight of any number of atoms. Because when you now say you want to know what's the weight of 1 million sulfur atoms, then you just need that number times 1 million. So let's make an example with a salt, with potassium nitrate, which is, by the way, a very important ingredient of any nutrient solution in hydroponics. You can see our formula: potassium nitrate, KNO3. You can see it is a salt of on the upper right corner here, of a positive charged potassium, which is a base, and nitrate is part of nitric acid, an acid, of course, with a negative charge. But at the moment we're just talking about the number of atoms. By the way, when we talk about the molar weight, we neglect that charge because the weight of an electron, which this has one electron more and that one is missing one electron, you neglect the weight of the electrons because in comparison to the other parts of which atoms are built, protons and neutrons, it's extremely low. So when we have potassium, we have 39.1, so we round these numbers. And we have 14 and 3 times 16. And we just need to add these numbers up, and then we have the molar weight of potassium nitrate. And what you should take away is 1 mole of potassium nitrate has 3 mole of oxygen. Because you can see that here, we take this salt, that molecule, as 1 unit, and we can have 1 mole of this, and in this mole we have 3 mole of oxygen. Okay? So another example, what do we have here? 2 atoms of nitrogen, 4 atoms of hydrogen, 3 atoms of oxygen, that is the salt ammonium nitrate. We have again nitrate, part of nitric acid, and we have ammonium. When you have ammonia, which has only 3 hydrogen atoms, it does not have a charge. And a hydrogen atom with a positive charge is only a proton. Because hydrogen, it has a proton, 1 proton, plus 1 electron. And if the electron is missing, it is H plus, basically a proton, and that reacts with ammonia to ammonium, and then it has a positive charge. So let's talk about the molar weight. We have 2 times 14, 4 times 1, 3 times 16 makes 80.04 gram. So ammonium nitrate, 1 mole of ammonium nitrate has 2 mole of nitrogen plus 4 mole of hydrogen plus 3 mole of oxygen. The same as the example before. So remember, the title of that first video is what is a molar concentration? So let's talk about what a molar concentration is, because we have now learned what a mole is. And I'd like to do that again at the example of ammonium nitrate. So a solution of 1 mole ammonium nitrate is a 1 molar ammonium nitrate solution. It's as simple as that, but I think you've already expected that. So if you have 1 mole of ammonium nitrate in 1 liter, then you have a 1 molar concentration. Okay, so it's not 1 liter plus 1 mole of ammonium nitrate. You need a certain amount of water, then you dissolve your salt and you fill up to 1 liter, and you do that in a flask to be precise. And this is what you write on the bottle: 1 m, this is a big M, ammonium nitrate, and you can write AQ in brackets. But that's a little bit old-fashioned, I think, and most people don't do that. And of course, 1 milliliter, it contains 1 millimole of ammonium nitrate. Because if you have 1 liter, you have 1000 milliliters. And if you have 1 mole by 1000, you have a millimole, of course. And this is what a molar concentration is. And we will talk in the unit of millimole when we talk about what is in the solution. Okay, guys, the moment has come. The first slide without our board, because I think you want to see something plant related in that moment now. And by the way, that nasty noise you have just heard in the background, it was boiling water, because I've just made a cup of coffee. I don't know how much mole of water that was, but it doesn't matter. So imagine you have some solutions like this is potassium nitrate, this is calcium nitrate. And by the way, these times 4H2O means that in the actual salt there are water molecules that exists. The same goes with magnesium sulfate. You have even a lot of water molecules in this. It's Imagine it like the following: there are sometimes different types of salts, and some they simply contain crystal water, but it's in a solid form. This is ammonium nitrate, this is ammonium phosphate, or this is potassium phosphate, potassium sulfate, potassium hydroxide, this is nitric acid, and this is phosphoric acid. But about pH and base and acid, we are talking about that later. And of course, our stock solutions, we call them stock solutions because we dilute them with water. So we take some water, we put in our nutrient solution, what we require, and then we fill them up to 1 liter or 10 liters, whatever. And you see, of course, we here have concentrations. So with potassium nitrate, you can use 1.5 because you require a lot of that, and then you don't need so much. I think you could do that with calcium nitrate too, but you know, on the other hand, it's always like you don't want to keep solutions too long. But you can do whatever you want basically. Normally, nothing happens when you stock them in a cool place. And then you see here our nutrient solution concentration. We take from that one and that one, we take 4, 4, magnesium sulfate, we take 2, and ammonium phosphate, we take 1. You don't have to worry about whether you make a stock solution including water in the salt or not, because you fill the stock solution up with water anyway. So basically, when you buy magnesium sulfate containing water in crystal form, then you bought some kind of solid water and you have to carry more. Because in case of magnesium sulfate, almost imagine half of the weight of the salt is water. Okay, factor just means 4 times 10. So if we want to make 10 liters, 5 liters, I just type in my calculator whatever I want and I know what I require to scale up. Okay, now let's take a look what is in a solution. So in a solution, you see here our element. So it's N, P, K, calcium, magnesium, sulfur. When we talk about pH, we talk about H plus or OH minus, but we come to that part later. So now, of course, our calculator, it adds up. Please focus first on that column with millimole. So what we have here is, you see, we have nitrate in this, okay? So we have a 1.5 molar concentration times 4 makes, I think it's 6, right? 6. And also the same goes for the potassium, 6. So we have 6 millimole of K and 6 millimole of N. This is all added up here. So you cannot see where the N comes from. You see the different forms of N, nitrate or ammonium. So in case of calcium, what we have learned, so you see you have calcium and you have 2 nitrates. So this normally this number here is written smaller here. Oh, where's my pointer? Here. So when we have 4 of 2N, we have 8, right? So in total, our nitrate is 14 because 8 plus 6 is 14 plus 1, that N, it comes from the ammonium phosphate. In total, your total N is 15. The charge of our ions, and I think I haven't said that, an ion is an atom that has a charge. So basically it's base or acid. at the moment we can ignore that part here. Of course, we can, we've learned we can calculate mole into gram and vice versa. So we can do the same with millimole and milligram. So we know we have 15 millimoles, then we have 210 milligram of nitrogen. And what I've just told you, we can do that with all these elements. And what you see here, that is part of the very famous Hoagland solution. This is a screenshot of the front cover of that publication. It's relatively old. It was a significant piece of hydroponic cultivation, and it's still used today because, you know, the basics or what plants uptake, it does not really change. Maybe you can change here and there a little bit, or you can adapt that for specific needs. Of course, I'm not saying that this is in general a solution that works perfectly for any plant in any development phase, but basically if you have that solution, it will have an EC of around 2. If you you can use that on cocoa, you can use that on potting soil. It will work. For the moment, it will work. What is going to happen with the pH when you use that, for example, in a recirculating rock wool system? Well, I can tell you from my own experience that the pH relatively quickly um, will go up. But the reason why that is happening, I'm going to cover that in a future video. Okay, the last column here we have NPK, because basically when you mix these salts, okay, then basically it is the same like when you have solid fertilizer and you mix that. So you can also calculate in percentage what the um, what the total nitrogen is in 1 liter. It's a little bit different whether you as a base for a calculation, um, whether you use the element forms or whether you use oxide forms, because the declaration of your fertilizer normally it is N is elemental and phosphor, potassium, calcium, magnesium, and um, sulfur. It is elemental and sometimes SO3, sometimes it is elemental. So this is why we have 2 numbers here, and the non-elemental form, they are called oxide forms. What I forgot to mention, of course, back then in the 1950s when the paper about the Hoagland solution had been published, they had already known about that micronutrients were required, including iron, of course. So now we are at the end of the first video about the pH series, and I want to talk about why that hydroponic series. And you have just seen what we've done. We have mixed our own solution, our own hydroponic solution with salts. Of course, when you mix fertilizer, they of course contain also salts. And what we're basically doing here is we control the solution, the initial solution. And this is the constitution, or this includes the EC. When you only have the information about the EC, you only know about salt content. But when we control the constitution, and you can calculate that with any fertilizer as soon as the declaration of your fertilizer is precise. This is including the pH, because the fate of your solution in any system is more or less what is left over from the constitution, because when plants uptake minerals, you have already seen that we're talking about base and acid. And what do you think? What happens when you have a solution right next to your root and the plant removes potassium or nitrate? Of course, it has an effect on the pH. And if you have the right stuff in your solution or the right elements, then you more or less can predict to some degree what your pH is going to do. So controlling the solution, the first part of controlling in hydroponics is the constitution of the solution. And as I've just explained, mole has a direct reference to the pH because we measure the pH in H+. You heard me talking about nitrate and nitric acid. A proton, or H plus nitrate, is nitric acid. And we get, when we uptake, for example, potassium, in return, we get H plus. So we remove a base, so the pH has to go lower, and we receive from the plant an H plus. But we will talk about pH later. In the next video, I'm going to cover pH more or less in a brief version because I don't want to bore you. This is not university, this is YouTube, and I don't want to make a video like 15 minutes about pH. Later, I want to do that. Okay, so I've just covered why that hydroponic series from a more or less technical point of view, from a hydroponic technical point of view, but I also want to talk a little bit about the background, why that's serious. So, in my opinion, the way hydroponics is approached is a lot oversimplified. That means you have pH numbers, you have EC numbers, you have ppms, milligrams per liter, MPK ratios, and so on and so on. But a lot of times in hydroponics, things happen, and people react to this by using more acid or changing the solution because they cannot understand what has happened. And this is why they don't have enough control over the solution. And my target is to open your mind what you have to do to understand what your system is doing. And I want to repeat that we had been talking about molar concentration today, and you have seen what a molar concentration is. And I want to repeat that mole or molar concentration has a direct reference to your pH. So with that said, I want to say thank you for watching, and like the video, subscribe, and feel free to leave a comment. Bye bye.